Hi. This morning I checked the fermentation to see how it was coming along, and it's coming along well. But it occurred to me it might be interesting for you to see how I can say it's coming along well, but I can also determine that it isn't finished yet. So what I'm going to do is I'm going to go inside here and we're going to take a look and see what's going on with the fermentation. One little warning is that you should try to minimize the opening and closing of this container, because obviously there's a chance that you could introduce contamination. It's less of a threat as you get farther and farther along in the fermentation, because initially we placed a fair number of yeast, grams of yeast in here, and after a few days we've built up a huge bioload of the desirable yeast. And we've also now started to accumulate some somewhat toxic alcohol, as well as eaten up a bunch of the sugar. So even though the risk of contamination is the same each time we open it up, the potential effect of the contamination becomes less and less as we're moving nearer and nearer to the final conclusion of the fermentation. So I'm going to open this up and we're going to take a look inside, and I'm going to show you a few things to look for. Now the first thing that you'll notice is that there is no foam. And part of the reason for that is because much of the sugar is gone. There's nothing much to support a foam inside of here. In addition, there's a sharp smell that comes off of here. It's a pleasant smell. It smells a little bit like beer, a little bit like whiskey, a little bit like breakfast cereal. It brings back memories of that movie Taxi Driver. So if you know the scene I'm talking about, you'll know what I mean. But in any case, one of the things that you can do in a poor man's chemistry analysis is use your senses in order to determine what's going on. The first thing, besides seeing no foam, is that smell includes a tang to it. And that tang, that bite, is due to the carbon dioxide. When the carbon dioxide gets on your moist mucous membranes, it forms a small fraction of carbonic acid, which is tangy, a little bit like lemon juice, or citric acid or acetic acid in vinegar. It gives that bite to anything that's carbonated, and you can smell that, so you know that CO2 is being given off. The other thing that you'll notice if you look very, very closely, and I'm not sure the camera is able to focus on the surface, but you'll see a very, very subtle fizzing. Those are the very tiny bubbles that are rising from the surface of the liquid. And so it means that the fermentation is still continuing. We're still eating up sugar. In addition to that, I'm going to hold my microphone, take my little lapel mic off here, and I'm going to try to hold it closer to the bin, and we'll see if you can actually hear the fizzing. I can hear it with my ears. Now another thing that you can do for testing purposes is taste. Because as the first wash was produced, we produced a fair amount of sugar. And the sugar makes this liquid very, very sweet. Tastes like sort of watered down breakfast cereal. There's still a little bit of sweetness, but you can now start to taste the tang of the alcohol too, the bite of the alcohol. But it's still sweet. So we know we're not done because of the bubbles, we know we're not done because of the CO2, and also because of the residual sweetness. The final thing that we can do is we can test the density. If you remember from the last time, we had a specific gravity of 1.06. And if you look at this meter here, that is the specific gravity. They've left out the 0 in front. So it's 1.010, 1.020. And that's a specific gravity above 1, which represents water. Now over here, this other scale, if you look and you'll see percentages, that is the percent alcohol that would be available if, for example, you floated this, this hydrometer in the liquid and it floated around here. You would end up producing approximately 7% alcohol if all of it were converted into alcohol. That's about where we were when we first started about 3 days ago, at about the 7% level. As the alcohol is converted, the sugar converted into alcohol, this will begin to sink lower and lower because the specific gravity of alcohol is lower. You'll find at pure water and alcohol, this would be way over the scale. It'd be way up here. But because there's residual dissolved solids in here, we'll never, ever, even if we convert all the sugar to alcohol, achieve the density of pure water. We won't get down there, but we'll get close. And so the potential 7% that we could get to, right around here, if we converted all of it, will probably not be achieved. We'll probably get somewhere around 7 minus 1 or 7 minus 2. 5 or 6% may be extractable. Now the trick to using this is put it in the cylinder first, because that way you'll know how much liquid you want to add and you don't end up pouring it over the top if you add too much or too little and it doesn't float. Now I'm going to fill this thing up. Hopefully I won't make too much of a mess. And we'll see where this floats. Remember, it was 1.060 before. I'll go a little more so we got to make sure it's completely levitated here. Now, another little trick is sometimes there are dissolved bubbles on this hydrometer, so you want to make sure you get rid of the bubbles that could potentially be floating it. And then you want to dip it down a couple of times to try to get it away from the sides, because that can also give you some false readings. If you look here at this, that blue, you'll see that our density is about 1.010. Make sure it kind of levitates. And at 1.010, that means that we've got about 1% potential alcohol that could still be gained. If I turn this around a little bit so the camera will show it, I'll show the specific gravity. You can see 0.990. Water would be right at that line that I have, that I'm supporting this at right now. And if I let go, we're very close to completely converted. It's a little frustrating to see it on the camera. You'll see that it's floating a little bit below the blue. And if we take this out just for a second, the place where it was floating was right about here. So we're very, very close to full conversion. We've only got probably a 0.5% more alcohol that we would gain if we drop this down and let it go down. You can see that it's bouncing right about 1.005. Okay, so it's been about 24 additional hours of fermentation, and I have a pretty strong suspicion that this has been completed. So what we're going to do is we're going to take a look inside of here, and then we're going to measure the specific gravity and see if we've converted that last little bit of sugar into alcohol. So take off our little seal. Try to avoid shaking the container, because the debris on the bottom, we don't want to get that up into the distillation. And if we're gentle with this, we won't churn up a lot of the material at the bottom. Okay, no chipmunks in there. And based on the smell, the sharpness is faded a little bit, so I think we are probably complete. And I'm not seeing a lot of fizzing or any bubbles, so again, I suspect we're probably there. So what we're going to do is we're going to get our little hydrometer. Now if we look here, let's see where this guy is floating. Oh yeah, okay. So we're at 1.001, 1.000. That would be 1.000. So basically, we are at complete conversion. And the only reason, as I said before, that we're not below 1.000 because of the fact that we have alcohol and water, which would be a lower density, is there are some dissolved solids in there that are not fermented. And so you're rarely ever going to get below the 1.000, which is pure water. So what we're going to do is we are going to fill our 4-gallon or 16-liter pot. And the way I'm going to do that is I'm going to use gravity to do this. And I'm going to siphon off some of this liquid into here, with the idea that I'm going to be pulling it from the top with this tube in order to try to avoid adding any of the debris that's at the bottom. Now if you have, say, a 4-gallon still, you probably at most want to put about 3 gallons, maybe 12 liters in there. You don't want to fill it up to the top, because there's inevitably going to be some foaming that occurs when you put this in here. And that foaming is not such a good thing, because it can actually push it right out of the still and into your final product. So you want to avoid the foaming, and the best way to avoid it is to make sure that you have a lot of headroom above the liquid. Don't worry, this is all going to be boiled, so don't worry about the contamination here. Now, as you can see, I'm filling this up, and then I'm carefully looking in the container here to make sure that my draw tube, what I'm pulling the liquid from, is as close to the top as I can get it. It's a little difficult to see it, but when you get near the end, you can almost see a little tornado, a little whirlpool forming. And you don't want to obviously suck in air and break your vacuum. But the higher you leave this, the purer the mixture is going to be. Nevertheless, you'll still see some foaming in there as this is pouring in. And that's the potential risk when you do the distillation. If you're in a hurry, a lot of that can end up getting pushed up through the still and into your final mix. It's not a disaster. If that happens, you simply have to empty your containers, and you're going to end up having to put it back in here and do it again. But if you're very slow, you're very patient, generally speaking, you'll get away with that. Another way to prevent this is just make sure that your pot has a much larger capacity than you're going to fill it with, so that you have a lot of headroom for that foam to break while the boiling process occurs. All right, I'm going to break this siphon. As you can see in the bottom here, we've still left a fair amount of liquid, and you could probably get a little more out, but I don't want to get that into the pot. It's just going to lead to more foaming and actually some off flavors. Yeah, that feels like about 12 liters. I'm going to put the bell on here, and some moonshiners will actually use dough or cornmeal and water to seal this. I end up using polytetrafluoroethylene or Teflon tape to do that work. This silicone tubing is not actually guiding the hot vapors, but acting as a connection between the two pieces so that they hold together rather than just depending on friction. Excellent. Put our thermometer in here, and then if you look down there, you can see that I commandeered our heat exchanger from our previous video on the solid state freezer. Took it up here because it is so effective and it's quiet. When you saw our brandy video about a year ago, I used a small heat exchanger, produced a lot of noise, and a lot of people complained about it. This is quieter and about 4 times as effective. It flushes water in and out of this container here where the spiral of copper is located that cools off the vapor as it's coming out. And then eventually it comes down through here, which is a silicone tube that is lined with essentially a Teflon or a polytetrafluoroethylene coating so that it's good for food and for ethanol content. So let's go ahead and fire this guy up and get him started. Now the secret here is slow. If you get impatient, what you'll find is that foaming that generally occurs because of the debris and the dissolved solids in here really only seems to occur over the first few minutes of the distillation. And so if you can move through that zone very slowly, it tends to break down, and then you get a very stable result. But that transition, once you get to around 170 Fahrenheit, around 80 centigrade, which is where you're starting to get the vapor forming up here, that's when you really want to tweak this temperature down and creep through that zone. And the first indications that you have that you're going to be producing something is you're going to get a few small drops of the initial liquid, which will contain some methanol, and we'll get into that in a little bit. So let me leave you for a few minutes while we get this thing close to temperature, and then I'll get into some of the details about how to get this thing started and how we're going to do the separations. See you in a little bit. All right, it's been about 20 minutes, 30 minutes or so, and the temperature has risen here. You can see that we're up to around 85, 86 degrees centigrade, which is above the boiling point of methanol. When the fermentation occurs of the sugar, with the yeast of the sugar, there is a little bit of breakdown of pectin when you're using fruit, or cellulose when you're using grains, and that will be broken down into methanol, which is toxic. It also has the highest vapor pressure, or the lowest boiling point, and it will end up being the first thing that is separated out of the mixture. A typical rule of thumb is that you'll get about 2 or 3% of your final distillate as methanol. And because it comes out first, that means you want to throw away about the first 2 or 3% of what you're going to end up producing. Now remember, we added about 12 liters and we expected to get about 1/14 of that in pure alcohol. This still will provide about 120 to 130 proof maximum concentration of alcohol, and an average over the entire distillation somewhere around 100 proof. So we should be expecting to get about 2 liters of final volume out of here. 5% of 2 liters is 100 cc's. So to be conservative, what I'm going to do is I'm going to dispose of the first 100 milliliters of liquid here, which is primarily methanol. There'll be a tiny bit of water in here, there'll be a tiny bit of ethanol, but we don't care. We're going to get rid of that because this is toxic. You don't want to drink it. You could burn it, but you don't want to drink it. Now, a little trick I've got here, I don't know if you can see this little tray, but because we're using a heat exchanger that is depending on air temperature to keep the water in this bath cool, the liquid that's coming out of here is at room temperature or tepid. And ethanol still has a significant vapor pressure. It evaporates at room temperature. So to save our precious ethanol and prevent it from evaporating and still have the open containers that makes this easy to work with, what I did is I took a tray of water and placed a metal grid in the bottom of this. This is the same material that we used to build the shelf in our freezer video. And put about 3 or 4 liters in here, put it in the freezer and froze it so that I have a block of ice that's going to be sitting on the table underneath my beakers. The reason for the metal is that this will allow me to put the beakers in here and keep them on top of the surface so that they're not tipping and tilting because it's filled with a bunch of water. And I'm also able to use a large quantity of ice so that over an hour or two this remains icy cold. The heat that's taken out of the beaker, out of the Erlenmeyer, means that the walls here are going to be extremely cold. And because they're cold, any additional vapors that want to make their way out of here are also going to be condensed, and we're going to retain most of the ethanol. Now, in order to get a very good thermal contact, I'm going to add an additional quantity of water to the top of this bath. And this is primarily just to provide contact surface with the beakers, so they're not just sitting on a couple of points in the ice. And I found this is very convenient because then the beakers don't tip. The Erlenmeyers are nice because they tend to be very stable, and they have gradations here that allow us to measure. Now, as you can see, we're getting near the 100 milliliter point, and once we get to that point, I'm going to begin doing the cuts. Even though we have a thermometer in here, I really don't depend on the thermometer other than to warn me we're getting near the point that we're going to start producing liquid. Because what we're going to do is once we start producing this liquid, we're just going to slice little bits of the distillate into individual containers, and then when we're done with the process, we can take our sweet time to mix and select what we're going to end up wanting to put in the final container that we're going to age to produce the whiskey. So we're getting close to 100. Once they hit 100 here, we're going to hit number 1, and we're going to begin with the material that we're actually going to save. Okay, it's been about 45 minutes to an hour worth of work, and I've accumulated about 9 samples of the distillate. And in testing I've found that the concentration of the alcohol goes down with time. And when I tasted, I found that as we moved further along, the flavor was becoming a lot stronger, but also it was beginning to get a little bit gamier near the end. And I elected to stop saving the material that I'm going to end up using for the aging process at number 9. If we look, this is not really debris, but it is additional material that we're not going to be using. In testing these, I've discovered that I like the flavor of all of them. The first component of any distillation breakdown is what's called the 4 shots. And that would be present in, say, the first beaker here. It contains a very high concentration of alcohol. As we saw, it was around about 100, I think it was 140 proof. But it also contains a lot of esters and aldehydes and can be kind of a harsh flavor. So we're not going to use this. Again, we can add this to a subsequent distillation and pull some of that alcohol and some of those flavors out, so we don't really need to waste it. But we're going to be using all of the rest of these in the aging process. And so right now what we have is a very raw whiskey. It's got some very interesting flavors, but it's harsh. And in order to create something that tastes very nice, we want to age it. Now, to create what's called a true Scotch whiskey, we got to be in Scotland, and we aren't. And in order to be called at least a whiskey, we've got to age it for at least 3 years. So we're not going to do either one of those things, but we are going to produce a Scotch-style whiskey type of beverage. And the way that we're going to age it is we're going to do a sort of an accelerated version of what's done in an oak barrel. What happens when you take this whiskey and you put it into a barrel? What will happen is that the barrel, the oak in the barrel, will impart additional flavors. And the most sought after type of barrel will be a barrel that contains or has been used to age sherry. And that the flavors that are available from the sherry are then imparted to the Scotch as it ages. And an interesting physical phenomenon occurs that when you place the liquid into the barrel and you place it in an unheated room or shed, the diurnal variations in temperature will cause the liquid inside, the alcohol inside, to expand and contract. And as it does so, it will be pushed into the walls of the barrel when it warms and pulled out of the walls of the barrel when it cools. And as a result, you'll get a constant inflow and exudation of the liquid in and out of the wood, and that imparts the additional flavors. That's why you don't want to temperature control it. One of the disadvantages of a barrel, though, is it has a very large volume to surface area, and so it takes a long time to do the aging process because of that disadvantage in terms of just geometry. So to accelerate that process, what we're going to do is we're going to place the liquid into a jar, and in the jar we're going to take oak that we've treated in order to make it like the oak that would be in a typical barrel. Now the way you do this is you get white oak, not red oak, white oak, and you can age this by placing this into an oven. And there's a very nice expose about this process done on a channel called Still It. It's by a New Zealander that's very much into distilling. And I'd highly recommend taking a look at his channel because he goes into a lot of detail about the temperatures and the duration and the effects on the flavor. And we'll put a link in the description below this video to his channel. You might want to take a look at it because he goes into a lot of detail. What we find is that as we age or as we toast the oak in an oven, it will become darker, it will begin to carburize, it will change some of the molecular structure in the oak, and it will darken. And depending on the temperature, we will impart different types of flavors to the final whiskey. Now, what I did is I experimented, as per his video, at several different temperatures, and I found that the temperature that seems to produce the nicest flavor, in my opinion, is 220 degrees centigrade, or about 430 degrees Fahrenheit for 2 hours. And then what you do is you run the temperature all the way up to broil, and after about 15 minutes you'll begin to get a slight amount of smoke that enters into the oven. That will create the outer char that we're looking for, which creates a charcoal which acts as a filter in that process of the infiltration and the exudation of the liquid that's moving in and out of the oak. Because of the fact that we have these little 10 centimeter strips and they have a large surface area, if we place these 100 grams of chips or sticks into a bottle, we can then add the alcohol to this and age this over a period of months instead of a period of years. Now, particularly, one of the things that I found is that you can use these very inexpensive ball jars, but I find that the alcohol will find defects in the plastic, eventually get through to the metal, and you'll get some rust spots on here. I much prefer to use these Fido jars, and you can get them on Amazon. They're about $8 or $9 a piece. They contain, or they hold up to 2 liters, and we've got 100 grams of oak in here. So what we're going to do is we're going to add all of the distillate that we have here into here, and we're going to soak this. Now, we will not have the advantage of that diurnal variation in temperature pumping the liquid in and out. We'll have to depend on just the random diffusion, because once these oak sticks become saturated and the air has been dissolved from here, we no longer can compress the air volume inside the oak, and so we won't force the liquid in and out. But what we will do by placing this in a warm environment is we'll increase the molecular interchange or exchange, and this will cause the aging process to accelerate. I don't think I'm going to get all of this liquid in here. I'm going to need to use another bottle for this process. But after a couple of days, you can begin to taste the raisin flavor, the fig-like flavor in this, the nutty flavor. It's a very nice quality. And because these jars depend on a rubber seal and all glass, there's no component that can rust, and therefore you're not going to get any problem with the jar itself. You can mix these, you can shake them up a little bit, and even within a few minutes, you'll begin to see that color develop. After about a week, you'll see this. This is some of the low temperature, I believe this was a 180 degree toast. This was a 220 toast. And within about a week, you begin to get a very nice rich color here, and you can begin to taste the flavors. So this is just starting. This is about a week into it. You can taste this every so often, decide when you want to start it, stop it. There's no real problem in adding a lot of oak. You could just, it'll go faster, you'll get more surface area, and you can speed up the process. A couple of caveats here. Obviously, follow your local laws. There are certain areas where it is not legal to do distillation, and so if you're doing an actual distillation of actual ethanol, you need to make sure that you're compliant with your local laws. But in any case, I've gone over the physics of the process, some of the little tricks and techniques that you can use if you're going to do distillation, and hopefully you found this interesting. In future videos, what we're going to do is we're going to look at different types of still designs, higher reflux stills that have a higher filtration capability, higher flow capability. We'll also look at distillation that not only is used for drinking beverages, but also distillation for chemical processes, because some of this can be used to drive a laser or can be used to power a vehicle. And so hopefully you found it interesting. If you did, take a look at our other video on distillation that we did about a year ago, and let people that you know that might be interested in this know about the channel, because we really appreciate the recognition and the broader exposure of what we're doing here. Also, comments and thumbs up will help in the promotion of our videos with YouTube's algorithms. And so I want to wish you a very happy afternoon, and stay safe, have fun with science, and we'll see you soon.